Hello, this is STA2023 Statistical Methods, Chapter 7, Section 2, Measuring the Quality of a Survey. So, statisticians evaluate the method used for a survey, not the outcome of a single survey. And two big things we want to talk about when doing a survey are bias of a statistic and the variability of a statistic. Now, these are two totally different topics, and they get confused a lot. So, the bias of a statistic is how close the samples are to the true population mean. How close they are. If the samples are close to the true population mean, they have low bias. If the samples are far from the true population mean, they have high bias. Now, variability is a completely different topic. Variability looks at the spread, how spread out the data is. If the samples are close to each other, you have low variability. If the samples are far from each other, you have high variability. So to kind of understand this, we're going to give you a visual representation of what's going on. And we're looking at the sampling distribution, the probability distribution of the p-hats, the sampling proportions. And so again, here's those definitions, bias and variability. Remember, bias is how close the samples are to the true population mean, and variability is how close your samples are to each other. So let's say the average of all part-time employees is $8. We'll call that $8 bullseye. And if you ever play darts, usually bullseye is the best thing. So let's call the true population mean the bullseye. And then these circles, these are like our darts. These would be our samples. These would be our samples. And we're going to talk about bias and variability separately, and then we'll give some numbers to make sure this makes sense. So our samples are here, our population mean is here. So notice that the mean, population mean is here. The samples are far away from the population mean, far away, so we have high bias. High bias. But they are close to each other. The samples are close to each other, so they have low variability. An example of this would be getting paid $20, $21, $22, $20.50, $19. These are far away from the $8 of what it's supposed to be, the true population mean, but they're close to each other. The next one, again, samples are far away from the true population, so we have high bias, but in this case, they're also far away from each other. So they're far away from each other, so we have high variability. So an example of this would be, remember, this is $8, 20, 50, 75, far away from $8, but they're also far away from each other, 20, 50, 75, 100. That causes high bias, high variability. Here, the true population is in the center, and the samples are all around it. So we have low variability, low variability. The samples are close to the population mean. And looking at the samples, they're close to each other, so we have low variability. So this would be an example of $8, $9, $8.50, $10. They're close to the 8, and they're close to each other. Now this is the one that people get confused on. So let's start with variability. Start with variability. The samples are far away from each other, so we have high variability. Okay? Now, are the samples close to the population mean, or are they far away from the population mean? That's the question, and this is where people get a little confused. The answer is we have low bias. Why? The samples are around the true population mean. They're around the true population mean. So it's not a bias problem. The problem is with the variability. We have high variability. So this would be like, excuse me, 2, 15, 9, 1, 20, 5, 8. They're around $8, but they're far away from each other. And the average of this would be around $8. Another quick example would be that if I was going to go buy a car, the average price of a new car, let's say, is $25,000. So that's the population mean. And if I go out looking for a car and the cars I like are $50,000, $53,000, $51,000, $52,000, $51,500, $52,500, they're far away from the true population mean, high bias, but they're close to each other, low variability. Okay? Now for the next part, there are three big ideas that I need you to understand. Three big ideas. And big idea number one, statistics vary from sample to sample. So if I ask one group of people, I'll get a number. But if I ask a different group of people, I'm going to probably get a different number. They may be close, they may be far apart, but statistics will vary from sample to sample. So I did a quick little survey here of the class, and you notice that it changed. Not much, but it did change. So different samples give different results. Big idea number one. Big idea number two. the size of the population does not affect the precision. This is the one people have a little bit of issue with, because they're like, doesn't the size of the population matter? It does, but if your population's large, you're good. If your population's large, then you're good. So I'll come back to big idea 2. Big idea 3. Big idea 3 says, large samples produce more precise estimators. And people are okay with this one. If I was going to ask 5 people versus 50, which is better? 50 people, more precise. If I was going to ask 500 instead of 50, which is better? 500. Or 5,000 versus 500. 5,000 is better. 50,000 versus 5,000. 50,000 would be better. So the larger the sample, the more precise the estimator. So we kind of get that. But the problem we have is the population. So it's the size of the sample. The larger the sample, the better the estimator, the more precise. It's not the size of the population. And that's what number 2 is talking about. The population is important. Yes, if your population is large, then you're good. But it doesn't matter if it's large like the size of New York City or large like the size of Orlando. As long as your population is large, it does not affect the precision. What does is larger samples produce more precise estimators. So let you kind of think about those 3 big ideas. Now, we're going to look at standard error, and here's the formula for standard error. It's standard error equals the square root of p times 1 minus p all over n. Remember, p is your population proportion, n is your sample size. And then notice there's some conditions. Condition 1, you can use this formula as long as your sample is random, and your population has to be greater than 10 times your sample size. So if I want to use that formula, I'd have to pass these 2 conditions. Number 1, is it random? Check. And is your population, which in this case is 1,000 people, greater than 10 times your sample size? Your sample size is 100. 10 times 100 is 1,000. Now, that usually never happens that they're the same. We're going to go ahead and let it pass, but your population has to be greater than 10 times your sample size. Therefore, we can find our SE. Now, when you find your SE, be very careful. In this case, your P is 0.25. 25% of the population are cat people. So it's 0.25 times 1 minus 0.25 divided by n, which is sample size of 100. Sample size of 100. Put this in your calculator, square root, or I'd recommend typing it in at once, but this is very important. Please practice this, that you type this in and get 0.0433. Make sure you practice that. Again, I recommend typing square root of 0.25, 1 minus 0.25 in parentheses divided by 100. Practice that. Practice that. In the standard error, it's kind of like your spread. Okay? In real life, we only get 1 chance. In simulations, we can repeat the survey many times to understand, but in real life, we only get 1 chance. We've got to be careful on bias and precision. We want to make sure we get the right outcome, and then we have the estimated standard error.